What I would like to do now is, having got this in 3 dimensions, we will ask now, can we do this in d dimensions? Can we write down the solution to Poisson's equation, or at least the fundamental Green function, in d dimensions? After all, this is del squared operator and its Fourier transform is minus 1 over k squared, and that fact did not depend on the dimensionality, because it just said take del and operate twice on e to the I k dot r. So I could have started by doing the following. So in d dimensions, in d spatial dimensions, and this is very important because the Coulomb potential or the del squared operator appears in all sorts of equations, and we would like to solve it in all dimensionalities. By the way, in 1 dimension the del squared operator is trivial, it is just d2 over dx2. And what does it mean to say that a function is harmonic in 1 dimension? What does it mean? It says you have a function of x and it says d2f over dx2 equal to 0. What does this imply for this function f? It is just a linear function, it is just a linear function, there is no curvature, this function is just linear. So f of x is some ax plus b. Okay. What it actually means is that the value at any point is the arithmetic average of values situated symmetrically about it. So the value here is the arithmetic average of these 2 values, as you can see from this triangular construction. So f of x is f of x minus a plus f of x plus a divided by the difference between the 2, divided by 2. Okay. This follows because there is no curvature. Had this function been convex or concave, had it been like this or like this, that would no longer be true. The value in the middle is not the arithmetic mean of these 2. Now this property is generalized to other dimensions. When you say that you have a function del squared of f equal to 0, what you are really saying is that the value at every point is the arithmetic average of values symmetrically situated about this point in the region in which this function satisfies this del squared f equal to 0. Because for instance, if you look at it in 2 dimensions, here is x, here is y, and you are saying del square d2f over dx2 plus d2f over dy2 equal to 0, what you are really saying is the following. A value here, you could take a point here, a point here, a point here, a point here in this fashion, and then if I rewrite these in terms of finite differences for infinitesimal separations of some kind, then this is the difference of the difference. So what it's really saying is that f of x comma y equal to f of x plus delta x y plus f of x minus delta x y plus f of x y plus delta y divided by 4. If I start with this and say this value is the arithmetic average of these 4 points, and now you can see I move the 4 to that side, and then I get f of x plus delta x minus f of x, and that is going to go in the limit to the first derivative with respect to x, similarly first derivative with respect to y, and then this is going to appear with a plus here. So it is the difference of first derivatives which gives you a second derivative, and eventually you end up with this equation. So if you start with this, you can end up with this in the limit. But this thing is completely spherically symmetrical, so circularly symmetrical, because you could have chosen this, this and this. In fact, you could have chosen all these points, and the arithmetic average of the integral of this function over that circle is the value in the middle. This is the property of harmonic functions in any number of dimensions, this mean value property. This does not mean that the solutions to this are linear functions of x and y. That is the richness of the whole thing. In 1 dimension the only function which satisfies that is a linear function. Now something which is linear in x and y would satisfy this equation of course, but you have a much greater possibility that this may not be 0, that may not be 0, but they could cancel each other. So that is how you get all this huge spectrum of harmonic functions which are highly non-trivial as the dimensionality increases, but they all satisfy that mean value property still. Okay. Now the consequence of this property is something like Gauss's law in electrostatics. It says you take the flux around the sphere and whatever is inside there, the charge or whatever, it tells you something about the charge inside. So now let us see what this says for the Coulomb potential in d dimensions, and which we define to be the inverse of the Green function, which is -1 over k squared. Let us see what it says. So I have del squared g equal to delta function d dimensional of r. So let us call this vector r, and this g is a function of this r. It is in any number of dimensions, so I will put a wiggly line underneath to denote a vector, and the integral that I have finally to do is 1 over 2 pi to the d integral d dk e to the I k dot r divided by k squared. This is the integral I have to do. As usual, it is sensible to use spherical polar coordinates, but let us look at what happens in 2 dimensions first. In 2 dimensions, what is this d dk? It is k dk d phi. Phi is the azimuthal angle 0 to 2 pi, the polar angle, and that is it. What happens to this? This thing is bounded and you get a k dk and you get a k squared, and the integral runs from k equal to 0 onwards. What has happened? Does the integral exist? No, not as it stands. It blows up. So it says in 2 dimensions we are in trouble. This is formally infinite. There is something wrong. This is formally infinite, diverges in 2 dimensions. Okay. In 3 there was no problem because this had a k squared dk and that cancelled this. In 4 this would be even better to have a k cube dk and so on, and that would be good, no problem. But in 2 dimensions we are in trouble, and this trouble is occurring for this Green function for small values of k. K is like a wave vector, or if you look, I think in terms of photons, it is like the frequency because these two are related to each other. So this divergence in field theory is called an infrared divergence. It is happening for small k or small frequencies or long wavelengths if you like. On the other hand, had the divergence occurred because k goes to infinity, it would be called an ultraviolet divergence. This terminology has come from obvious connections with photons, but that is a standard terminology. So what we have discovered is that the Green function for the del squared operator has a formal infrared divergence in d equal to 2, but for higher dimensions it is okay, 3, 4, 5 etc. it is okay. So let us try to do that in higher dimensions first and then come back and tackle this 2 dimensional problem. We would like to choose spherical polar coordinates in d dimensions, and what sort of coordinates do you have? In 3 dimensions of course you had k, a theta and a phi. This ran from 0 less than equal to k less than infinity. This guy ran 0 less than equal to theta less than equal to pi, and this ran 0 less than equal to phi less than 2 pi. Those are the usual spherical polar coordinates. What happens in d dimensions? Higher than 3, 4, 5 etc. How do you define these polar coordinates? Well, in exactly the same way as this thing here. It turns out it is exactly the same as this. What you need is a k which would run 0 less than equal to k less than infinity, that is the magnitude, and then you have a theta 1, a theta 2 dot 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 up to theta d minus 2. So in 3 dimensions you need just one. These are the quote unquote polar angles, and these guys all run 0 to pi, and then there is a phi which runs as before, 0 less than equal to phi less than 2 pi. Okay. These are called hyperspherical polar coordinates. It's a big name, it just says in higher dimensions you have generalized whatever happens in 3 dimensions. Okay. And what is the volume element? This quantity d dk gives you first a k to the power d minus 2, d minus 1, and then there is a sine theta 1 to the d minus 2, because remember in 3 dimensions it was just a sine theta d phi, but in d dimensions it is sine theta 1 to the d minus 2, and then there is a sine theta 2 to the d minus 3 dot 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 all the way to sine d minus 2 to the power 1, and then you have a dk d theta 1 d theta d minus 2 d phi. That is the volume element in hyperspherical harmonics. So what I would like to do is to put that in and play the same trick as before, namely choose this r, choose the polar axis along r, and then k dot r becomes k magnitude r times cos theta 1, and all the other angles can be done, all these things can be done, the integrals can be done, because eventually you just have powers of, you have things like 0 to pi d theta some sine theta to the power r. This is a known integral, converted 0 to pi over 2 pi over 2 to pi, and then of course this integral can be done fairly easily. This happens to be equal to root pi, you can write this down, it's a special case of a beta function, it is root pi gamma of r plus 1 over 2 over something or the other, I do not remember, but this is doable, you can write down the answer. So we can do that for every one of these guys except this, because here you have an exponential factor also, and then you have to do the k integral itself over the magnitude of k. So it is not an altogether trivial task to do it in an arbitrary number of dimensions, higher dimensions. You can do all these integrals except the theta 1 and the k integral, and one should first do the theta 1 integral. The answer turns out to be some Bessel function which involves little k, and then you have got to put that in along with this k to the d minus 1 factor and integrate over k from 0 to infinity. That too is a standard integral, and we can read it off the tables or something like that. But what I want to emphasize is, okay, this is a strict way of doing this if you know the tables of integrals, but we would like to give a little physical argument and do this problem in an easier way. And above all, whatever we do, it will be a function of d eventually, and we should have to deal finally with the fact that when you put d equal to 3 we should recover minus 1 over 4 pi r certainly, and when you put d equal to 2 it should diverge, should be a problem, and there should be a way of getting a finite answer, because we know that in 2 dimensions the Coulomb potential is actually well defined. What is the Coulomb potential in 2 dimensions? How would you define this? Imagine you have an infinite line charge and a parallel line charge, 2 parallel line charges. What is the potential between them? It is logarithmic, right? If they are infinite, then you can take any section and it is independent of where this section is taken, and the force between these two, attractive or repulsive, goes like the log of the distance between the two, right? So in 2 dimensions I expect the Coulomb potential should be log r, whereas in higher dimensions it is some power, inverse power of r, and the answer will actually turn out to be 1 over r to the power d minus 2. So in 3 dimensions it turned out to be 1 over r, apart from the 4 pi factors and so on. So this would be the Coulomb potential in all d greater than equal to 3, and at d equal to 2 it switches to a logarithmic potential. 2 is called a marginal dimension in this case for this operator. We should be able to extract this information. In particular, we should be able to derive this relation fairly straightforwardly. So what I will do next time is to give you a simple physical argument which will help us deduce this along with the factors that go with it, and then see how to handle the d equal to 2 case. Okay. We will use a method which does analytic continuation treating the dimensionality d as a complex number. It is called dimensional regularization, and it is a famous method in quantum field theory, which is the reason why I thought it is worth talking about it even in this elementary example of the del squared operator. So it turns out that you can make sense out of these formally divergent quantities by treating the dimensionality of space as a complex variable. So doing things as a function, analytic function of d, and then extracting information from this analytic function. We will see what happens when we go to d equal to 2 explicitly and see how dimensional regularization operates. There are other ways of extracting this information, but we will do this and then check it out against other methods. Okay. So we start at this point, here, and I try to evaluate this exactly using a simple physical argument and then check out whether the right limits emerge at d equal to 3 and so on. And the point was to try to do this in ultraspherical coordinates in which you have a magnitude k and then you have d minus 2 of these polar angles and one azimuthal angle which you can integrate over. Okay. When you do this, what happens finally is that this whole thing reduces to a certain integral after you do all the angular integrals, which I have given in detail there. But after you do all that, you end up with just one integral over the magnitude of this vector k, and that integral looks like this. So apart from some factors which I do not remember, there is an integral which is 0 to infinity dk k to the power d minus 4 over 2, and then a Bessel function appears here of the first kind, d over 2 minus 1 of kr. So the whole thing, this is some constant times that. The whole thing reduces then to doing this complicated integral over a Bessel function with an order which is some fractional order, d over 2 minus 1, and then a power of k sitting here. And the question is, what is the value of this integral? Now this also can be done, this integral can be done, but let us see what we can say about the integral without doing it. Okay. The first point is that this integral does not exist for all values of d. Okay. As you can see, you would like it to converge at infinity, and you would like to make sure it does not have too bad a singularity at the origin due to the integrand. Okay. Now what are those criteria? And depending on whether those criteria are satisfied or not, we can make an assertion as to where does this make sense as a function of d, as a function of the dimensions d. Now this sort of argument where we just count powers is called power counting, and it is fairly powerful in most cases, but in this case it is not going to work fully, it is going to work partially, and I will explain why this is so. First point is that let us look at the behavior at infinity. Now when does an integral like integral up to infinity dk k to the power r, when does this integral converge? Clearly it does not converge for any positive power r, converges only when r is negative, so you have it in the denominator, and in the denominator the power should be at least bigger than 1. If it is just 1, you get a logarithmic divergence, right. So it is clear that this integral is less than infinity if r is less than minus 1. Minus 2, minus 3, or minus 1.5 is fine, but minus 1 leaves you a logarithmic divergence. Okay. Now what is the behavior of this thing for large values of k? Well, you have a power of k sitting here, and you also have some k dependence sitting here, but the Bessel function has the property that whatever be its order, when its argument becomes extremely large, this function goes like some oscillatory function, sine, cosine, etc., divided by square root of k. So the power k is minus half in such cases, and then in this problem r is equal to d minus 4 over 2 minus a half, whatever be d. because it depends only on the argument here and goes like 1 over square root of k, and that is it. So we would like to have this quantity, this is equal to d over 2 minus 2 minus half, that is minus 5 over 2, to be less than minus 1. Okay. And what does that say about d? Over 2 less than 3 over 2, or I should now put in this real d less than 3, because if d is complex, has treated as a complex variable, the fact that it has an imaginary part is irrelevant for this power counting, because they will only lead to oscillatory terms. So as you know, in all such cases here it is really the real part of this index r that matters, and real r must be less than minus 1 or real d less than minus 3. So even d equal to 3 is not allowed if we went this route. On the other hand, we did integrate d equal to 3 explicitly, we got this answer here. But I remind you that in doing that we were faced with an integral that did not converge absolutely. We ended up, just to remind you, this thing involved integrating 0 to infinity dk, there was a sine kr over k. This integral does not exist in the absolute sense, because if I take absolute values, then this is bounded by 1 and you have a dk over k and it diverges logarithmically at this point. So this integral exists only because the sign of kr changes sign, it takes plus and minus values, and you know that this sinc function leads to a convergent integral, because at the origin at k equal to 0 it is this, and then it does this as a function of k, starts at r, this thing here at k equal to 0, and then it oscillates down in this fashion. So the envelope of this function, that dies down like 1 over k, it is this thing here, and that alone is not enough, it does not die down fast enough, it actually would diverge logarithmically. But because this function oscillates in sign between plus and minus values, there is some cancellation between the contributions from the plus and minus side, and these areas cancel out against each other to some extent and then lead to a convergent answer. We know the answer here, this is equal to pi over 2, this thing for all positive r it is equal to pi over 2. So already we see the symptom of the disease, and that is the one that we have identified here, because it says real d less than 3, and this power counting does not take into account the fact that this function changes sign back and forth. It is as if the whole thing just went down like 1 over square root of k and nothing more than that. So that was the reason, and we will keep that in mind. We will see what happens when we get the exact answer in a very short while, but I want you to bear in mind that this integral formally does not exist for real d greater than 3 or even equal to 3. Okay. So it barely made, d equal to 3 barely made it. Okay. So there is a divergence, and this divergence happens formally for very large values of k. Now there is a terminology borrowed here from field theory, which is when such an integral diverges for large k, that is like large wave number or large frequency equivalently, it is called an ultraviolet divergence, because as you know ultraviolet is a higher frequency side. So this integral has an ultraviolet, formally has an ultraviolet divergence for d greater than or equal to 3. What happens at the small k limit? Well, something else happens. At the small k limit, we should ask, when does this integral converge? And what would be the answer? Once again, any positive value of r now is perfectly alright, there is no problem. Even a negative value is alright as long as it is not more negative than 1 over k. The moment you have a 1 over k, you have a log 0, and log 0 is infinite, and when you have 1 over k squared it becomes very bad, and so on. So this power r should be greater than minus 1 this time for it to converge, right. So there should be real part of r greater than minus 1. The inequality is reversed in this case. But now you could ask, how could this integral, so if I really formally gave you a thing like this, does this ever exist? Would this ever exist at all for any value of r? No, of course not, because at the lower end it says r must be bigger than -1, at the upper end it says r must be less than -1, and you are finished. In both cases you are finished. But now we are saved by the fact that the behavior of this function is going to be different for small values of k. This thing still goes like d minus 4. So in this case r is d minus 4 over 2, no problem there. But you see, the Bessel function itself for small argument depends on the order. And if you recall what the definition of this Bessel function is, j nu of z is a summation n equal to 0 to infinity z over 2 to the power nu plus 2n over gamma of nu plus n plus 1 n factorial and a minus 1 to the power n, which disappears when you have the modified Bessel function. Whatever it is clear that for small z the leading behavior is z to the power nu, the n equal to 0 term, that is the leading term, and that goes like z to the power nu. Therefore, for small values of k near k equal to 0, this integral goes like k to the power d over 2 minus 1. So you add that here plus d over 2 minus 1, and this must be greater than minus 1, this thing here, and that says d, in this case real d, must be greater than, and what do you get? You get a d that is 5, what did I do? Oh sorry, there is a 2 here again. So there is a 2 plus 1 3 minus 1 is 2, real d greater than 2. So we see that this integral, this thing here formally, you can write this down, power counting I should not say power counting alone. We did a very simple minded power counting. We did not take into account the fact that the integrand can oscillate in sign and so on. So this is a sort of naive power counting. So let us call it naive power counting, implies that this integral is convergent, integral convergent in 2 less than real d less than 3. So now I am regarding this integral as a function of d, a complex parameter d. Okay. Of course my physical interest is in d equal to 2, 3, 4 etc., but I am regarding this formally mathematically as a function of a complex variable d, dimensionality d, and then this integral is defined, well defined by power counting in this region, in this strip between real d equal to 2 and 3. The physical points of interest for me are things like d equal to 2, 3, 4 and so on, but the 3 we have already evaluated. Now I want to see what it does for general d, and it looks like the whole thing makes sense only for d between 2 and 3 in this case. So here is what is done. One says, all right, very good, I will evaluate this integral in the region between 2 and 3, get the answer as a function of d, this complex variable d, and analytically continue to other values of d if I can do so, and then claim that that is the correct answer for all d. This is what the beginning of something called dimensional regularization is, and it also says something else. It says if you should face a singularity somewhere, throw away the singular part and keep the part which is non-singular at any value of d at all. So now what do you expect? We expect that for d equal to 2 I expect a divergence of some kind, and d equal to 3 I expect another divergence, and this is an ultraviolet divergence, and this is happening due to k going to 0, small k, small wave number or large wavelength, a small frequency, and the natural term to use is infrared at this point. This is called an infrared divergence. Okay. So the technical term for such a singularity is called an infrared divergence at the lower end, and an ultraviolet divergence at the other end, and this guy seems to have both. There is an infrared as well as an ultraviolet divergence in the problem. So we really have to examine this a little further. Where this comes from, we know it is very clear due to small and large k behavior respectively, and we need to know how to deal with it. Now what the prescription of dimensional regularization does, this is a technique used in quantum field theory for making sense out of apparently infinite integrals, but here you've chosen that method of regularization just because we know something about analytic functions and analytic continuation, and secondly it illustrates the general idea here, as you will see. So this thing here is called the technique is called dimensional regularization, and in a nutshell it is the following. We evaluate these integrals, divergent integrals, in the region in which they are convergent, regard the answer as an analytic function of the dimensionality d, and then analytically continue to your dimension of interest, whatever is of interest to you, and should there be a singularity like a pole, you throw away the singular part and keep the regular part at that point, and that gives you the value. That is the prescription. And now let us see whether it makes sense here, and then I will try to give a physical argument which will actually say why this prescription works in this particular case. Okay. Now the first step is to actually evaluate this integral, but now that requires a table of integrals to do this thing here. I am not going to do that, we will short circuit it because I can get the same answer by a much simpler direct argument, and we will do that without even using Fourier transforms. I just go back to this equation and observe that I want a solution which is spherically symmetric. That is very important, and the reason is I want the fundamental green function. Now this equation here itself, the equation itself is translation invariant. So if I shift the origin, the coordinate, it does not matter at all. It is a function of r minus r prime here. The delta function here is a function of r minus r prime, and my boundary condition is also a function of r minus r prime, because it says it goes to 0 as r goes to infinity, which is same as r minus r prime goes to infinity. Because of that I know the solution is a spherically symmetric one, but let us write this thing out by integrating over both sides over a hypersphere of radius capital R. I am going to regard this equation as Poisson's equation for a static charge, a unit charge if you like at the origin in some suitable units, and I use Gauss's theorem. So let us integrate over a hypersphere of radius r both sides, and what does this give you? It says dv and then del dot del g d, that is what del squared is, then del dot del here is equal to an integral dv delta d of r vector, and that is equal to 1 because you are integrating a unit impulse function, a delta function, over a sphere of radius r, and the answer is 1. There is a unit charge inside the sphere. But I use Gauss's law here. Use Gauss's law for this guy, and what does that tell you? It says the volume integral of a divergence is the surface integral, is the flux of this vector field. So this is equal to an integral ds rather del g d dot ds. But I want the spherically symmetrical solution. So this del g is like a force now, the electric field, and that is radially outwards, right, and therefore del g dot ds, the scalar product, there is no cosine here because ds, the unit normal, points outwards, this force also points outwards in the same radial direction. So I could directly write this as equal to whatever that force be, so it is dg d over dr. This is the normal component. By the way, the radial component of the gradient is just the derivative with respect to the coordinate, the magnitude, that is dg d over dr times an integral ds over a hypersphere of radius r. This is exactly like doing Gauss's law, using Gauss's law in electrostatics to find what the electric field is for a spherically symmetric distribution. You take a Gaussian sphere with the same center of symmetry and then you say argue that the field is normal, outward normal, parallel to the unit normal to the surface area, and therefore the field comes out, it depends only on the radial coordinate multiplied by the surface area of the Gaussian sphere. That is all I am doing here, except that this fellow here, so this is dGd over dr times this is now the surface area of a hypersphere of radius capital R in d dimensions. In 3 dimensions it would be 4 pi r squared, in 2 dimensions it would be 2 pi r, and so on. So clearly in d dimensions the answer is proportional to r to the power d minus 1. Right. So this multiplied by, and the answer is 2 pi to the d over 2 r to the power d minus 1 over gamma of d over 2. Okay. So that happens to be the surface integral which gives you the surface area of a unit sphere of radius r. We just have to check that this guy is going to give the right answer for the cases we know. If you take d equal to 2, then this is 2 pi and gamma of 1 is 1, and that is 2 pi to the power r, 2 pi r, which is the circumference of a circle of radius r. If d is equal to 3, then it is 2 pi root pi, it comes from here, and then there is an r squared, and this guy here is gamma of 3 halves, which is half gamma of half. Gamma of half is square root of pi, so that goes away against the root pi here, and then the half here multiplies this and gives you 4 pi r squared. So it is okay in these cases, and that is the general answer here. So now we are there, because we find now that dg d over dr as a function of r is equal to, because this integral is equal to 1. So it says dg d over dr is just gamma of d over 2 divided by something or the other, 2 pi to the d over r to the power d minus 1. Okay. So we have used ultraspherical coordinates, but we use that not to do a k integral, but to write this down, to write the value of this integral down. Okay. So you can't get away from doing those angular integrals, but this is a much simpler geometrical problem. Okay. By the way, what would be the volume of this thing? We found the surface area. What would be the volume of this sphere? The question I am asking is, we found SD of r, we have written as 2 pi to the d over 2 r to the d minus 1 over gamma of d over 2. What is the volume Vd of r equal to? It would be the integration up to whatever radius you want, right. Similarly, you differentiate the volume with respect to the volume, you get a radius and you get the surface. Okay. That is the very definition of volume. Okay. All right. So here we are. Now the question is, what is this equal to? But we need to impose a boundary condition, and our boundary condition is that g should be 0 at infinity. So let us integrate both sides. We will integrate from r to infinity dr prime, just to avoid confusion, dg dr prime over dr prime. This is equal to g d of r with a minus sign, because it is 0 at infinity, so I throw away that portion. That is my boundary condition, and that is equal to gamma of d over 2 divided by 2 pi to the d over 2, and then an integral from r to infinity dr prime to the power r to the power 1 minus d, r prime to the power 1 minus d. It is the integral of this fellow here. and that is an integral which is trivial. So it says GD of R is equal to gamma of d over 2 over 2 pi to the d over 2, a minus sign, I got to be careful, I move this minus sign to the right hand side, so there is a minus sign, and then an integral of this here. At infinity it vanishes, and why? Why does it vanish at infinity? Well, let us do the integral. What is the integral equal to? It is r prime to the power 2 minus d over 2 minus d, and says r prime equal to r prime equal to infinity. And why do I say it vanishes at infinity? D is greater than 2. I can't get away from that. The integral makes sense only in the region d greater than 2, definitely. So I have to keep d greater than 2. Otherwise it doesn't make sense. So no matter what trick I use to do it, I do need to keep that. That's what we found earlier, that you had a serious infrared divergence, and therefore this integral is equal to minus gamma of d over 2 divided by 2 pi to the d over 2, and then the only thing that contributes is the lower limit of integration with a minus sign. Now I will kill that minus sign against this 2 minus d and write it as d minus 2. So d minus 2, but the other one remains, no question about it, and then r to the power 2 minus d, which I will write as 1 over r to the power d minus 2. Okay. And that is the answer, that is the exact answer, and it is an analytic function of d, as you can see, and we know where its singularities are. And what is the most obvious singularity of it as a function of d? There is a simple pole at d equal to 2. So we said right away there is an infrared divergence in this problem at d equal to 2, and indeed you see that at d equal to 2 there is a singularity at this point. So as it stands, this expression does not make sense for d equal to 2. First of all, if you put d equal to 2, you get an infinity here, you also get a constant here, so it says there is no r dependence, but that we know is not true. Right? There has got to be some r dependence in the green function. So it is clear this formula is not right at d equal to 2. There is a singularity and we need to deal with that thing. Is there a singularity somewhere else? What about this gamma function? What happens if d is 0? There is a pole. There is a pole of this gamma function. What happens if d is minus 2? There is again a pole. So this thing has the green function of the Laplacian operator appears to have singularities at d equal to 0, minus 2, minus 4, etc., but mercifully we are not living in minus 2 dimensions, right. So this is not of physical interest to us. It is there, formally it is there, but we are not worried about it. But d equal to 2 we are worried about, because we do have planar problems and we need to know what to do about d equal to 2. But let us first settle the infrared, the ultraviolet divergence. Is there a singularity at d equal to 3? No. What happens if you put d equal to 3 here? Well, it is minus, and then there is a gamma of 3 over 2 that is equal to half square root of pi divided by 2 pi square root of pi, and then there is an r minus 1 over 4 pi r, which is right. So you see you have recovered the d equal to 3 result completely, and there is no ultraviolet divergence in the problem. For that matter, you could put d equal to 4 or 5, and you get the analog of the Coulomb potential in those dimensions, and it is clear from here that the analog of the Coulomb potential in d greater than or equal to 3 dimensions is 1 over proportional to 1 over r to the d minus 2. So in 3 dimensions the Coulomb potential is 1 over r, but in 4 dimensions, if you lived in 4 spatial dimensions, the Coulomb potential is 1 over r squared, and the force would be 1 over r cubed. So whatever role is played by the inverse square law in 3 physical spatial dimensions is played by the inverse cube law in 4 spatial dimensions, and inverse 4th power in 5 dimensions, and so on and so forth. Okay. Now you begin to see also why Gauss's law works in 3 dimensions for the inverse square law potential, because you see the surface area increases like r to the d minus 1, and if your force also decrease like 1 over r to the d minus 1, the two will cancel each other and give you something, a flux which is independent of the actual shape, etc., etc. So this is why the inverse square law is so special in 3 dimensions. No other force law would have this behavior, this form of Gauss's law in vector calculus applicable directly to tell you something about what's inside. So it's very special. Now what have we done here? We have defined our Coulomb potential in any number of dimensions to be the solution of Poisson's equation, or rather the inverse Fourier transform of 1 over k squared, or rather the potential which satisfies Poisson's equation, namely the green function of Laplace's equation, the Laplacian operator. This is what we have defined as the Coulomb potential in any number of dimensions, and you see the special role played in 3 dimensions by 1 over r. Okay. Now let us come to d equal to 2. So no ultraviolet divergence in this problem, and we know the quote unquote physical reason why. We know that naive power counting is misleading in this problem because it works as long as your integrand has a definite sign, and in our case we had a Bessel function and it did not have a definite sign, it kept oscillating, and therefore the convergence is better than what naive power counting tells you. Okay. So we do not have to worry about ultraviolet divergence, but infrared, yes, to worry about this here. Now what is the prescription? Again let us go to the prescription of dimensional regularization and ask what is the prescription. By the way, this result you can get in d equal to 2 equally easily by writing down what is the actual potential for a line charge in 3 dimensions and using Gauss's law as you normally would for a static line charge. You can do that and you get exactly this, you get the answer immediately. What would you say is the answer here? This in 2 dimensions. Let us do this argument we did about integrating this Poisson's equation directly on both sides. So we had dg over dr in 2 dimensions over dr multiplied by the surface area of whatever was the unit sphere of radius r, and that in this case was 2 pi r, that is the circumference, that is equal to 1. That is it. So what does it tell you about G2? dg2 over dr equal to 1 over 2 pi r. Now what does that imply for G2? Apart from constants, you have to integrate this with respect, you get log r. So this is equal to plus a constant, depends on the boundary condition and so on, we will come to that in a minute, but it is this log r. And as you know, if you took two uniformly charged, if you took a uniformly charged line charge, for instance a static line charge, and asked what is the potential at an axial distance r from this line charge, the answer is proportional to the log of this distance in 2 dimensions. Well, that is exactly what you got here, you get a log. So what has been special about 2 dimensions? What is special is that when you integrate a power here, remember we integrated 1 over r to the power d minus 1, you got 1 over r to the power d minus 2. That is true as long as the power here which you integrate is not equal to 1. The moment it is 1 in the denominator, you get a log, right. So this apparently simple fact that the only power which gives you a log when you integrate is 1 over r, this apparently simple fact is profound, it is very deep. and it has all kinds of implications everywhere in the quantum Hall effect, in even quark confinement, etc., etc. But it is just that in 2 dimensions you have something very special happening, very and it is traceable ultimately to this fact here. But now let us see where we can get from our formal answer here by analytic continuation. What we are supposed to do is to take this answer and write out what happens to it near d equal to 2. So this is equal to minus gamma of d over 2 divided by 2 pi to the power d over 2 times d minus 2 r to the power d minus 1 d minus 2. And now I ask, what is it going to do, what is this guy going to do as d tends to 2? The leading term is a pole, and we can write down what this residue of this pole is. So this goes as d tends to 2, the pole is already sitting here. So to write the residue down in this pole, you have got to multiply this by d minus 2 and then take the limit as d goes to 2, which is the same as saying set d equal to 2 in all other factors. So this is equal to gamma of 1, which is 1, and then a minus 1 over 2 pi, it comes here, and then a d minus 2. That is it. That is the singular part at d equal to 2. So this is the singular part. Plus, now we got to look for the regular part. The regular part will have a term proportional to a constant, no d dependence, plus a portion proportional to d minus 2 to the power 1, and then 2, 3, etc., positive powers of d. We are interested in what happens as d goes to 2. Well, all you need to do is, apart from other factors which you can expand every one of these in a Taylor series about d equal to 2, put everything out, divide by this and ask what happens to this and compute this. But we are really interested in the portion that depends on r, and the only part that depends on r is sitting here. So write this guy as r to the power minus d minus 2 equal to e to the power minus d minus 2 log r, it is an identity, and expand this in a Taylor series about d minus 2, which is the same as saying expand it in a power series, you already are there, right. So you have a portion that goes like this factor. By the way, everywhere else we can set d equal to 2, so you get plus, you get a minus 1 divided by 2 and then a pi and then a d minus 2, and then taking this and expanding it, you get 1 minus d minus 2 log r plus order d minus 2 whole squared. And this cancels out. This portion we already have here, so I should not write it again. We already have here. So this whole thing goes to minus 1 over 2 pi times d minus 2. This is the singular part, plus 1 over 2 pi log r plus some constant as d goes to 2. The constant will not involve r, plus higher orders in d minus 2, and they will all vanish as d goes is set equal to 2. Now the prescription of dimensional regularization says throw this away, that is the singular part, it does not involve r in any case, and you are left with 1 over 2 pi log r, which we know is the answer, is a green function apart from a constant. Now the point about this constant is that, as you know, in a 2-dimensional problem, even in the problem of the line charge in electrostatics in 3 dimensions, you cannot choose the potential to be 0 at infinity. This particular problem, that boundary condition can't be chosen because it is going on, the charge distribution itself is going all the way to infinity, in some direction. So you can't choose the potential to be 0 at infinity. What do you do in the case of elementary electrostatics? You say, well, I know the potential at some particular point at some radial distance, and I say the difference in potential between the potential there and where I am is proportional to log rho over A, where A is the distance of the point whose potential you know. So you say rho minus rho of A is proportional to log rho over A, log R over A, okay. And that is exactly what happens here. So the operative point is that the operational point is that in 2 dimensions the green function is proportional to the log of R, okay. And dimensional regularization has given that to us neatly in one shot in all dimensions. It's immediately given, okay, including the 3D answer, and then it also says what happens at 4, 5. It says there is no ultraviolet divergence in this problem, only an infrared divergence, which does exist because there is a singularity, and that happens essentially because d equal to 2 is a very special dimension where this integral happens to be log R. So where a power law changes over to a logarithmic law, you will always have this sort of problem in general. These are called marginal dimensionalities, and they have lots and lots of very interesting properties, and in 2 dimensions this is one of the interesting properties.